Good morning, and also big thank you to the organizers for inviting me. This really seems like to be a very nice conference with very interesting talks. I really look forward to all the talks. So I'm also happy to contribute a bit to this. And I'm going to talk about quadratic enumerative invariants and local contributions. That's the title. So let me try to explain the title just with one example. And the example I picked is one of the simplest examples you can do. Or one of the first examples also. It's the example of lines on a smooth cubic surface. So let me start with some history of this enumerative geometry example. In 1849, Cayley-Salmon already showed that the number of complex lines, let's call this surface X, L inside of X, is always 27 when you take a smooth cubic surface. So this is a classical result in enumerative geometry. So what happens now if I'm only interested in the lines which are actually defined over R? That's something that was already studied by Schläfli in 1863, and he found that there could be 3 real lines, and the rest is pairs of complex conjugate lines if the cubic surface is defined over R. There could be 7, there could be 15, or there could be 27. This depends on the real smooth cubic surface. So this always equality doesn't hold here anymore. However, in 1942, Segre had a closer look to the real lines on a smooth cubic surface and classified them. He found that there are 2 types of real lines. Which he called hyperbolic and elliptic, and also looked at what happens in these different cases and wrote down how many of them are hyperbolic and elliptic. And we actually don't know, no one knows if he actually saw the following, but it follows directly from his work that the number of hyperbolic lines minus the number of elliptic lines is always 3. So here I can put always again. And this is now independent of the smooth cubic surface you pick. And finally, Jessica and Kass-Wickelgren, I think it was published in 2021, showed that, maybe I can move this up, showed that for K, a field of characteristic not equal to 2, then there is if I have a type of a line defined over L, then if you have a line defined over if you have a line defined over K, then there's a type of L in the Grothendieck-Witt ring of quadratic forms. And if you take the sum over all the lines in your smooth cubic surface over these types of the lines. This is not quite it. We also consider lines which are not defined over the base field K, but they might be defined over some finite separable field extension. Then you have to trace down. And then we can also say the always here, and what they get is 15 times 1 plus 12 times minus 1 in the Grothendieck-Witt ring of K. So maybe I should say this type lives in the Grothendieck-Witt ring of the field of definition of the line. Okay, so the plan I made for today is to actually compute this 15 times 1 plus 12 times y minus 1 in brackets in the Grothendieck-Witt ring. And I thought it would be nice to use Marc's result from yesterday, Marc's localization result, to actually compute this. This was not computed using Marc's localization result, but you can compute it like this. So I want to do this. And then I want to, there's also something about local contributions. What do I mean by local contribution? In this case, I really mean the type of a line, and I'll explain to you geometrically what this type actually is. So that's for the second half of the talk. So that's the plan. So I thought I would start with a very, very quick explanation of this formula, everything in this formula. So what is this GW of K? And now for today, let's just assume that the characteristic of K is not equal to 2. And let me just, I already said that there's the elements in there are isometry classes of quadratic forms. But let's do a shortcut and just say that this is additively generated by symbols, these brackets, where A is a unit in K. And this bracket, if you want to think about it as a quadratic form, it's the quadratic form which, or the isometry class of the quadratic form, which sends, well, sorry, x to a x squared. And we have a couple of relations in here, namely ab squared is the same as a for ab units. A times b is a times b. A in brackets plus b in brackets is the same as a plus b in brackets plus ab, a plus b in brackets. Now here we also want that a plus b is not equal to 0. And let's put a fourth relation. A plus minus a is always 1 plus minus 1. And we call this H for hyperbolic form. So, okay. Here I also have some trace. So if you have L over K, a finite separable field extension, then we get the trace homomorphism from the Grothendieck-Witt ring of L to the Grothendieck-Witt ring of K. And what is this? If you have a quadratic form over L, you can just post-compone with the field trace, and this gives you an element of the Grothendieck-Witt ring of K. But what you need to know for now is just that this thing here exists. Then maybe one more thing. We also have a rank homomorphism from the Grothendieck-Witt ring of K to the integers, which just sends one of these bracket A's to 1. Or if you want to think of this as quadratic forms, this really sends it to the rank of the quadratic form or the dimension of the vector space it lives on. And finally, Marc also yesterday introduced at least the Witt sheaf. Now let's just go to K. The Witt ring of K is just the Grothendieck-Witt ring of K, and you mod out by the ideal generated by H. But by the fourth relation, this is really just all the integer multiples of H. So in order to compute something in the Grothendieck-Witt ring, we could just compute its image in the Witt ring and its rank, and then put both of them together, and we'll get something in the Grothendieck-Witt ring, and that's how we will do this today. Okay. That's all I wanted to say about the Grothendieck-Witt ring. That was very, very quick. If you're not familiar with this, are there any questions? I can also do more examples. Everyone seems to be happy. Okay. So now okay. Okay, good. Probably. Okay. I'll just put the hair away. Okay. So now let's go back to this example. How can we compute this? So for this, I want to let this GR24, I think I will write G13 be the Grassmannian of lines in P3. So if I have a line in P3, I'll get a point which I just denote by I put the brackets around it in the Grassmannian. Then I have a vector bundle over it. First of all, I have the tautological bundle, which I call S, but I actually want to take the third symmetric power of the dual tautological bundle. So this defines a vector bundle. And let me just tell you what the fiber over the point L is. This is just degree 3 homogeneous polynomials on the line L. So what does this have to do with this problem? If you have a smooth cubic surface defined by a polynomial, homogeneous polynomial in 4 variables, so here, so this is of degree 3 for cubic surface, then this is a smooth cubic surface, then this gives rise to a section of this vector bundle. So let me call this section sigma f. And what does it do? It sends the point corresponding to a line to f, which was of degree 3, restricted to a line. So we get degree 3 homogeneous polynomial on the line. Now, what are the zeros of the sections? That's when f restricted to the line vanishes, or in other words, the line lies on the cubic surface. So the zeros of this section are exactly the lines on the cubic surface. So if I want to count the lines on X, I could just instead count the zeros of the section. And how can one count the zeros of the section? This can be computed as computing the degree of the top Chern class, or Marc called it Euler class yesterday, of this vector bundle. So this is the top Chern class, or Euler class. No, just let me tell you, I will compute this with Bott's residue formula in a second, but you could also do this with Schubert calculus, and you actually get the 27 from this. So that's how you can get this one. Now, I could also rearrange this as write this as 3 times 1 plus 12 times h with this h here. And I told you to get the 15 times 1 plus 12 times minus 1, or the 3 plus 1 plus 12 times h, we need the rank, which is the 27. And we need the image in the Witt ring, so we just delete the 12h, so we also want to get the 3 somehow. And how do you get the 3? Well, yesterday Marc told you about Borel-Moore homology with coefficients in the Witt sheaf, and we can take this an Euler class. There's also an Euler class there, so we can also look at the Euler class of this in Borel-Moore homology. Will be different 0. With coefficient in the Witt sheaf, and since this is relatively orientable, you don't need to twist this. So you can take the degree of this, and you'll get something in the Witt, and we will see. We can compute this, for example, with the localization formula, that this actually gives us this thing. So this is something I will compute now. Are there any questions? All right, otherwise so I want to put this, I want to put this all the way up. Let's see, then maybe, I can't do 2 at the same time. So now I will recall Bott's residue formula and Marc's version of it, the quadratic version of it, and do this computation, which will probably take longer than I planned, but yeah. Let's see. So now, recall from yesterday, let's do this classically first. Let's recall Bott's residue formula. So I will just do this with the torus. I just take GM. You could also take GM to the n, but let's just do GM. Let's assume this x on x. X will be the Grassmannian in a second. So in general, let this be a K-scheme. Let's assume that this action has, for simplicity, only finitely many fixed points. Let's call them P1 to Pn. And let's assume we have alpha in equivariant Chow groups of X. Then Watt's residue formula tells us that alpha is the sum over all the fixed points, so I from, or j from 1 to n, ij lower star, so ij is just, I call them p, j into x, of ij upper star alpha kept with the equivariant Euler class of here. This yesterday in the formula, Marc said it was the normal bundle, but we just have points, so the normal bundle is actually just a tangent space like this. So now let's assume this is in Chow 0, and we can take the degree. Then I can also take the degree of this, and actually then I can, the degree is just pushing forward to the point, so I can actually forget about this part. So we can just compute this instead. So let's do this in the example. So I want to compute the equivariant Euler class of this vector bundle. So for this, I need GM action on X, which is just the Grassmannian now. So in the example, now X is the Grassmannian, but let me first write down an action on P3. Namely, I want T to act on a point in P3 by here on x0 it acts with weight W0, then weight W1, and so on and so forth. Like this. And this actually gives me, it acts on P3, but then this induces an action on the Grassmannian. So now let's hope that we're in the good situation that we have finitely many fixed points, and that is actually the case. The fixed points are the points in here which correspond to the lines defined, let me call them Lij, by the vanishing of xi and xj. In particular, there's 4, choose 2 of them, which is 6. Oh yeah, thank you. So let's choose wi's. Like not all the same. Probably relatively prime is a good condition. Yeah. Otherwise, we would not have finitely many. But you have, you have all freedom to choose. Like you can choose them very, very big and far apart. Otherwise, alternatively, you could just have an action by GM to the 4 on it, and then you would have the same fixed points. But this looks more similar to the one thing I do in a second. That's why I'm doing this. Okay, so now we have these 6 points. So now we want to compute the degree of this Euler class, but now equivariantly. So this is the same as summing up over, let's just say I shouldn't be the same as j. So now I'm pulling back. So I'm taking ij upper star of alpha. Alpha is the Euler class. This commutes with taking the Euler class. So I can just take the Euler class of the pullback, which is just a fiber. So this is Lij. And here I have to devalue out by this guy. So how do you compute this? Let's just do one of them. So let's do L23. So this is the line defined by the vanishing of x2 and x3. So what is this fiber? It's the vector space with basis. It's the k-vector space with basis x0 to the 3, x0 squared, x1, x0, x1 squared, and x1 cubed. So we have a 4-dimensional vector space, and we have a GM action on it. But actually, the vector space just generated by x0 to the 3, for example, is invariant. So this splits up as a sum, and all of the other ones are too. So this splits up as a sum of 4 one-dimensional representations. So this is actually the one generated by this, direct sum, the vector space generated by this. Like this. And now, how do I compute the equivariant Euler class of this? I do the Borel construction with this and get a vector bundle over the classifying space of GM, which is just P infinity. But this vector bundle splits up as a sum of line bundles corresponding to this irreducible representations. And it will be just the following. You will see where these come from. No, that's this one. You just have to take the Euler class or the first term class of O of, so here we have weight W0, so we'll get 3W0 E of O of 2W0 plus W1 times E of O of W0 plus 2W1, or E is the first term class, E of 3W1. So this is just 3W0, this is 2W0 plus W1, and so on and so forth. So this turns out to be...
How is bundle defined on the classifying space defined?
How is this the one here?
Yeah, this gives you a bundle on the classifying space.
Yeah, you just do the...
It's not the trivial bundle on the...
No, it's not. It's not. So you just do this diagonal action. So you have EGM, and then you put this here over BG. You do the Borel construction.
This is, okay, but this is just a point, right? This R23 is just a point.
This is just a point, so that's why you get down here,
yes.
you just get the BGM. This is just doing this with a point.
Okay, yes, it's not tricky.
So now, here you just copy this for I and j, so you get 2WI plus WJ, WI plus 2WJ, 3WJ, and then you need to do the same for the tangent spaces, and I'll just tell you what this is. You take WI minus, so there's, if you have taken I and j, there's two more, so let's call them N and M, so let's say N, M, I, J, sorry, is 0, 1, 2, 3.
Maybe it's W0 and W. Oh, I see. You're doing all. Okay.
Yeah, okay. WI minus WN, WI minus WM, WJ minus WN, WJ minus WM. Like this. And now you can put this into a computer And all the w's cancel and you get to 27. I recommend doing this with the computer. Okay. Are there any questions? Is there a question? Okay. Then let's do this now with the n localization. Ah, yeah, sorry. I was, this morning I was struggling. It's like, I want that n, m, I, and j is 0, 1, 2, 3, so I get all of them. Yeah, okay. Let's put this here. And now let's do the exact same thing with n. So recall from yesterday that so Marc has a quadratic version of this. So now you want to replace GM by n. What is n? It's the normalizer of the torus in SL2. So you can put the torus, GM in SL2, by sending T to this matrix. And to get the normalizer, you need another generator, which is called sigma, which is this guy. And now, instead of taking alpha in the equivariant Chow group, we take alpha in the equivariant Moore homology with Witt coefficient. Yes?
So you computed this invariant and degree.
Yes.
So why is this the count of lines? I see that the number is the same.
Ah, yeah, okay. So that's something, so the count of lines you can compute as a degree without the equivariant thing, right? And then, well, we do this in the equivariant setup. Marc did this yesterday. So in degree 0, it's the same, and the one without the equivariant maps to the equivariant one. So that's why, and it's the same, yeah. But yeah, that's a good question. Yeah, should have said that. Thanks. Okay. So we want to replace this by n, and we get the exact same formula. So now let's move right on to the example. Now I can act on P3. How do I want it to act? I want, let me write it as. This guy act here as now t to the a, x0, t to the minus a, x1, t to the b, x2, t to the minus b, x3. And I guess I want to pick a, b, odd, and also coprime. Yes. And I also need to tell you how this sigma acts. And let this act by sending it sigma. It should swap the xi's with the sign. Let's send it to minus x1, x0, minus x2, minus x3, x2. So this also induces an action of n on the Grassmannian. And now the fixed points correspond to, we only have 2 fixed points corresponding, because these 2 are swapped. So we have the fixed points corresponding to the lines 0, 1 and 2, 3. So this is x0 is equal to x1 is equal to 0. And this is the line defined by the vanishing of x2 and x3. So now we want to do the same computation again, and let's just do let's do the same example again. Let's look at sim3 as dual L23. This is still the K vector space with spaces x0 to the 3 and so on and so forth. And now this again splits up as a direct sum of irreducible n representations, but now I have to, it's not 4, it's 2. It's the one with this, because these 2 are swapped by sigma and 0 squared x1, 0 x1 squared by this. Again, these give rise on the classifying space now of n. And now if I want to compute this, as dual, it will be a product of equivariant, not equivariant, Witt-valued Euler classes of something, yeah, it's A here. A, like this, and to look at the for this. No, here this is for this one. You get this.
Yeah, 3a, but the force action on x squared x1 is 2a.
No, here it's really, so it's 2a minus a.
You're right.
So it's 2a minus a gives me only 1a. Yes. For the definition of these, so these are the vector bundles coming from this irreducible representation, but here for this, I just see Marc's paper on here about localization for the definition. I don't know. And I also can just tell you what this is. This will be 3a times a times the Euler class, each of them e squared, so this is this thing which will cancel in a second. So now if I want to compute the degree of, no, the other way around. Do I put this on top? Yeah. And here, W here. Sim3. I just have 2 summands, and here we get 3a squared times e squared, which will cancel. Then for the tangent space, we will get a squared minus b squared. And the other one will be the symmetric thing. You get 3b squared, b squared minus a squared. And now you don't need a computer to see that this is 3. And you get the 3. OK, so 20 minutes for the time. Are there any questions about this computation? Yes?
On the first line of sim3 of the symbol with the bracket x0 squared, x1 squared.
This one?
Yeah, and the other one, why is it not the same as the one you did before, or is it just the notation?
Oh, so for the GM action, GM just sent x0 to t to the something times x0. It left it invariant. But now the n action swaps x0 and x1. So in order to find the invariant subspaces of this vector space, like these are swapped. so I can't separate them. So I get two invariant subspaces. Yes?
So in the previous example, you used the formula we all know about the top chart class of the sum of line bundles.
Yeah.
I think you're using here some formula for the Euler class in mid-cohomology of the sum of line bundles. What are you using here? What do you know about the Euler class?
About
In the second line. In the second line, you compute the Euler class of the sim.
here, this one.
No.
This one.
Yeah. You seem to use something that you know something about the Euler class.
Ah, this one. Okay, so that's why I say see Marc's paper. No, Marc finds all. It's a computation. Marc finds all the irreducible n representation which give rise to.
You're asking about you're taking the product, you're turning the sum of vector bundles into
product. That's just the Whitney sum formula. Just this.
Some kind of sum formula for the Euler class in mid-cohomology.
Yeah, it's the same Whitney sum formula. If you have a direct sum of vector bundles, it's the product of Euler classes. Ah, now I get it. Thanks. Yeah. Okay. So I was lying a bit there. Like there's an O plus and an O minus of A depending on how sigma acts. One of them is O minus, one of them is O plus. It depends a bit on the parity of A. It could also be the other way around, but then minus it would cancel. Yeah. Okay. Then I just want to say something. What else you can do with this? Because this you can also compute by hand without using localization. But how can I erase? Yeah.
So you need to have orientations to compute degree and so on?
Yes. I was also lying a bit here. So the thing is, this Euler class would live in here, and you have to twist by that minus of this bundle. Tensor omega. You have to actually twist by this, but this thing here, it's relatively orientable, so you can find an isomorphism to the square of a line bundle. So I'm just throwing this out.
If you change the orientation, it will change to multiply by some. I mean, you can always multiply by some.
Yeah.
You need to have some kind of canonical orientation, or.
Yeah, you need to choose one. Yeah, I think there's a rather canonical one. Yeah. You could also get -3, I guess, if you choose a different orientation. Yeah, I mean, yeah, I know you can because I've also gotten -3 by choosing a different orientation. So, yeah. Okay. So, more examples. In general, you can also do lines on a degree 2n-1 hypersurface in Pn+1. So n is the dimension of the hypersurface. So if n is equal to 2, you should get the cubic surface, and 2 times 2 minus 1 is 3. Good. So you can do this, and I'm sure now, I hope I didn't give you quite enough, but you might believe me that you can compute the quadratic version in the Witt ring of K as the Witt-valued Euler class of sim 2n-1 as dual over the Grassmannian of lines in Pn+1. And well, if you had like a sim 5 here, you would get another factor with O of 5a. So you would get 5 times 3, which is 15, and in general, you will get 2n minus 1 times 2n minus 3. So you take all the odd factors in the Witt ring. You could also do lines on complete intersections. But this is always relatively orientable. Here you have to actually be careful. Sometimes this is not relatively orientable. So this doesn't always work, but for the following example it works. You could do 2 degree 3 hypersurfaces. In P3, not P3, P5, sorry. And then what you get is you compute sim3 as dual plus sim3 as dual over the Grassmannian of lines in P5. What you get is this will give you a 3, this will give you a 3, so you get 3 times 3 is equal to 9. And one thing you could also do like this is what Marc also mentioned yesterday is instead of lines you could count twisted cubics also in hypersurface of the correct degree and dimension. For example, this works on a quintic threefold. And then what you get is 765 in Witt of k. And the way you do this is exactly the same as here, but much more complicated. So I'd rather want to do the computation for lines on a cubic surface. For this, you really need a computer. To get the rank, this method was in enumerative geometry to compute things like this was pioneered by Ellingsrud Strömme, who did the classical one, the not quadratic one, and they got so classically. So you get the rank, and then you can build your element in the Grothendieck-Witt ring, and they got 317,206,375. Okay. So, and for this you also need the computer. So let me talk a bit about the types. At least the cubic surface types I think I can do. So now what are we actually counting? Let me give you a geometric way of seeing what this type of a line is actually. Yes?
What did they do classically? What's this number?
So now what I did first with GM, they did the same with the GM action, and
In which case?
for the twisted cubics, they did this for the twisted or degree 3 rational curves. Yeah.
This is the real array.
So this is like the signed real result or the image in the Witt ring, and this is the thing in the Grothendieck-Witt ring. For example, the 3 times 1 plus 12h. In this example, it would be 765 times 1 in bracket plus this specific number minus this number divided by 2h. Good sign, right? So now I want to answer the question, what is this type L in the Grothendieck-Witt ring of the field of definition of L in the formula up there. So every line is counted with some quadratic form, and it's given by this type, and it has a really nice geometric description. For this, let's look at the Gauss map. Let's first assume that the field of definition of L is actually K, otherwise you just base change. Then let's look at the Gauss map. Let's call it G for Gauss map from L, which is just P1 over K now. And now we want to map to the two planes in P3 containing L. But if you stare at this, what this actually is, that this is actually parameterized by P1. So you get the map from P1 to P1. And if you write this down, you see that this map has, oh, I haven't told you what the map is. You send a point on the line to its tangent space in the cubic surface. So X is the cubic surface, the smooth cubic surface. And then you can send a point to its tangent space in the cubic surface and identify this with a two-plane in P3. And now you can write, you choose an equation for X and compute what this tangent space is, and you get that this is actually a degree 2 map by writing this down. So what does this mean? So this means that there are always 2 points PQ on the line with the same tangent space in X. Because it's a degree 2 map. And this gives you an involution. Let's call it I from L to L, which swaps these 2 points. It sends P to Q and Q to P. The fixed points of this involution are defined over, you might have to adjoin a square root of something, but they might either live over K, or you have to join a square root of something which is not a square. So you want to join something in units of K mod units of K squared. So identify 2 elements in here if they differ by a square. And if I join this alpha, this is well defined up to squares, which alpha you join. That's what I want to say. Yes. So now Jesse, Kass, and Kass-Wickelgren show that the type of L is just really, you take this alpha and stick it into brackets in the Grothendieck-Witt ring of K. And I said that alpha was well defined up to squares, but we have this first relation in the Grothendieck-Witt ring, this relation 1 up there. So this is actually well defined in here. Maybe let's do this over R. Well, let's say assume K is equal to R. Let's do an example. Then we get that there are two types. There, if K is R, I have two choices for alpha. I could choose it to be -1, and then this K joint square root of alpha would be the complex numbers, or I could choose it to be 1, and then both fixed points are just defined over R. So either alpha is equal to 1, bracket alpha is equal to 1, bracket 1, or bracket alpha is equal to minus 1 in brackets. So how does this look like geometrically then? Over R, if I take the real points, I get an RP1, which is just an S1, and it sits somehow in the cubic surface. So I have an S1 and it sits in the cubic surface. And what is this? What does this, now, okay, I have this S1, it sits in a cubic surface. Now I can look at the tangent space at each point, or I could just equivalently look at the normal vector and follow it around the line. So I get like a loop. In the end, I will end up at the same normal vector. And what could happen now is that I just go here, at some point I turn and come back, or I do like a full turn. That's the two things that could happen. If I go here and I stop and change direction, that means that I actually have a fixed point. So we're in this case. That's when I have just like it's just trivial. If I do like a full turn, we get this one. So that's like the geometric meaning of this. So now,
Which one is hyperbolic?
yeah, right. Let's go back to this up there. So this actually, alpha is equal to 1 is exactly what Segre calls hyperbolic. And this is what Segre calls elliptic.
So the elliptic means the normal bundle is in the real points is a Mobius.
It's not a Mobius band. You actually do a full turn. You end up at the same thing.
Oh, so it's an even.
It's even. It's
even.
yeah.
The other one is not.
No. Both are even. One is like you do this. You do a turn and you come back. You basically do nothing. And one is like you really do a full turn and come up here. They both look like the trivial bundle, but it's like if you follow like a frame around it, it's different. Okay.
Yeah, it's always O minus 1 is the normal one. So
It's always.
depends on
Yeah, right. That's also true.
depends on the pointing in one direction is the orientation.
Mm-hmm. Okay. Okay, good. So now my time is already almost up. So let's say in my thesis, so I generalized this to the type of a line on quintic threefold. So I did this in my thesis. I figured out what the type should be for a quintic threefold. And here, one could also do this for hypersurfaces, and this is joint work with Felipe is here. And Stephen McKean. We also do the type of a line on degree 2n minus 1 hypersurface in Pn plus 1. So there you can have a generalization of this description, but there's still a lot of open questions. For example, we don't know the type of a line on complete intersections. So in this case, I really don't know what we're counting. And also, for example, twisted cubics. No idea. Okay, so let me stop here.
Oh, thank you very much. Are there any questions? I have to give you the microphone if you want to ask questions.
Is it possible to generalize these things to, like, the counting problems on Grothendieck-Witt invariants?
I mean, which things, like the...
Oh, anything.
Anything. Well, I mean, for like general counting problems, one obstruction is, for example, this relative orientability, which is not always satisfied. So we really need this isomorphism to a line bundle squared. So many things you can generalize. This is one obstruction. I think for like virtual classes there are more obstructions, but I don't. That you should ask other people, not me. So many things, yes, not all of them.
Any other question? Yeah, I don't think I understand quite what you. I mean, the open questions. What is the type of a line? I mean, there is no. I mean, there is no involution in general, or whatever.
I already. If you. I don't know if this involution description is the correct one, but it's a nice one and it works here. So if you do this, for example, for if you try to copy this for a higher degree hypersurface, you just go to, like, in the next case, 3 planes in P4, you will already get to map to P2 and you don't have an involution, but you can still extract some involutions out of this. So in this case, for this thing here, you get involutions, and the involutions will give you the type. I think in general it won't be involutions. Like if you count other things than lines, I don't think it will be involutions, but I don't know what it is in general.
I mean, there's always a formula for the local contribution, but it's just some determinant or something. And I think the type is to give some geometrical, understandable. I mean, it's a vague notion.
So just to make sure I understand, so the type is the local contribution?
Yes, exactly. Yes, exactly. So up there, this formula, you have this sum over all the lines, and you have like this type, and you can just write down a formula. You just have like, you choose local coordinates around your point, or the point defined by the line in the Grassmannian, and you choose the trivialization of the vector bundle, and then you just take the determinant of the Jacobian, and that's your formula for this.
Yes. So the open question is to find nice formulas.
Yeah. The open question is to, what does this actually mean? What is this geometrically? I mean, I can write down the formula, but it's just a very abstract formula. You don't see any. It's just a big determinant you compute.
Any other question? Else we resume in some minutes. I don't know exactly how much, but